I know, don't worry. It's my house, they're probably like, hey, you pay 30.
All right, here we go. I think that should work.
No, not that one. There's like
I was going to, except I started in the wrong color. I don't know what's going on here. Sorry. I'm going to start over. All right, so the laws of logarithms. We're going to look at some of the rules that deal with logarithms. I think we'll have time to actually kind of work through them so you can see where they come from a little bit. But let's start with some basic stuff. A little bit of, I don't want to say it's a review. Sorry, guys, this is driving me crazy.
Sorry for the interruption. Can all of the grade 9 students come down to the auditorium for a brief meeting? Thank you.
Wow, that's exciting.
what are they doing?
I don't know.
Is it all grade 9? Yeah, no, I agree. It was a huge meeting.
Can we go down?
Hey, we're in grade 9. No.
He still hasn't got an email.
I sent it again. I don't know what to do. You could check his school email, maybe? I could send it there.
He said it'll just go on the YouTube channel.
Sure. Sounds good. All right, so let's start with this. We talked a little bit about this notation yesterday. It's one of those things that you kind of have to get used to a little bit. Once you get used to the notation. Sorry? Well, we're not actually doing any trigonometry, so it doesn't really matter. So, yeah, it doesn't. Yes, yes. So just a reminder from yesterday, we read this as log 64 base 4. The base here, the 4 is a subscript. The 64 is not. It's not an exponent either. It's just in line with the log. And just a reminder, this means that 4 to some exponent has to equal 64. And you would have done some of this in grade 11. You would have looked at how to solve these. And there were some for homework, yes. So, and Josh, you might be wondering, why is he doing this again if we did this for homework? It's just really all about the practice. This notation is brand new to you. I want to make sure that you see it over and over and over again so that hopefully, you know, it'll sink in and you'll get exactly what's supposed to happen here. So, yeah, you can do some guess and check here. We talked yesterday here about how we can take a little bit of a shortcut. If we can somehow write 4 to some exponent equals 64, is there some number that 3? Perfect, yeah. And we talked yesterday about how if we look at this equation, we have on the left side 4 to the x, on the right side is 4 cubed. They're both equal. The only difference in the writing on either side is that the one has an exponent of x, the other one has an exponent of 3. So in order to make those the same, x has to be 3. Let's try a couple more. So let's look at the log of 1/27th, base 3. So we can deal with fractions here. And again, if you're not sure where to go with this, we can always write it out in exponential form. This just means that 3 to some exponent has to equal 1/27. For now, yep. We're going to talk later about how you can actually eliminate the guess and check as a strategy. But for now, and this is very similar to the equations, the exponential equations that you would have solved in grade 11. We need to find some way to write the right side as a power with base 3. You might recognize that 27 is just 3 cubed. And we're kind of getting closer. We now have a base of 3, but this one's in the denominator. The one on the left is in the numerator. How can we, yeah, so we can actually just switch that around by making the exponent negative. It's on. Good thing I have you guys looking out for me. Again, the left side and the right side are equal. The only difference between them is that the exponents, here it's a -3 on the right and x on the left. So in order to make them equal, the x has to equal -3. So that's kind of a quick summary of not all of the homework, but certainly some of the homework. Here's one more. This one might stump you a little bit, or maybe not. Why don't you give that one a try? Right. Well, it's kind of all about the base, right? Yeah, so we... Tony didn't like that. Sorry, it wasn't that funny. Yeah. Yeah, so remember that if we don't write a base in, the understood base is a 10, and you could kind of think about that in your head, or if you need to, you could just jot it down. So if the base isn't there, this really just is base 10. So 10 to some exponent has to equal 100, and most of you can jump right here and say, hey, x has to be 2.
So if there's no base, then we assume it's 10.
Yes. Yeah, and that's what your calculator does. On your calculator, there's a log button. All of the work on your calculator that the calculator does is in base 10. Your calculator cannot do ones with other bases. But that's okay, you'll be able to. That's rough. So let's get into the laws of logs. I don't know, that's a good question. That's a good question. So you've seen so far that the logs are related to exponents. I mean, obviously, all of these questions we dealt with some exponents. So the laws of logs actually deal with exponents as well. So I think it might be worth looking at a few of these. I'll look at a few of them. We'll talk a little bit about why they are the way that they are, and then we'll get into some of the more complicated ones. Yeah, sure. Well, I'm going to keep going if you... Oh. I don't have anything. Sorry. So this is one of the laws. And again, I don't expect you to memorize this law. It's just think about what's going on here. What this says, it says that a to the 0 is equal to 1. Pardon me? Yeah, so anything to the exponent 0 is equal to 1. So it makes sense that this right here, a to some exponent has to be 1. It makes sense that that something has to be 0. Is that okay?
No.
It's not okay?
When you write log a1 equals 0, does that mean the exponent's going to be 0 or a? It means the exponent.
So yeah, and I know you weren't here yesterday, Leslie. This means that here's the base. Here's the exponent, and here's the result. So a to the 0 is equal to 1. Is that okay? Anything to the exponent 0 is 1, always, yeah. Well, okay, except for maybe 0. It's what we call an indeterminate form. Yeah.
Oh, okay.
Here's another one. I'm not going to fill in the second half. I mean, there's going to be an equal sign here, and we're going to stick something over here. But I want you to think just for a minute about what do you think this is going to equal? Oh, you changed your answer. Oh.
A is the same value,
Right. Right. So this means that a to some exponent equals a to the x. So if I write that down somewhere, a to some exponent, I'll leave it blank, has to equal a to the x. Right. Yeah. Yeah. I was trying to convince you not to go and change your mind. So this is just an a to the, I mean, it is possible to have a power here But in this case, it kind of makes sense. A to the x equals a to the x, right? And there's one more. This one's a little bit trickier to understand what's going on, but we'll get there. Here's an a to the log x base a. These are like different rules or laws that apply to logarithms.
Is x resultant or is a still a subscript of log?
Here it is, yes. So this whole log x base a, this is an exponent. So this says that a to some exponent, and in that case the exponent is the log. I know this is really kind of confusing. There's a couple ways that we could look at it. Yes. Yeah. What do you know about the exponential function and the logarithmic function? They are inverse functions. And what does that mean? Think of another pair of functions and inverse functions for a second. Think of the easiest pair of inverse function pair that you can think of. What have you got? Oh, yeah, okay. That's simpler than I was thinking. But that works. I'm not sure it will demonstrate my concept to you. Even better than sine. Sine could work. Think about x squared. What's the inverse of x squared? No. Well, this is an interesting discussion here. Sorry, I'm going to just change the page here. Y equals x squared looks like this. What does the graph of the inverse look like?
It looks like this.
Looks like this? So we said? And I guess technically down here too, right? But if we do that, it's not a function anymore. What function is this? Yeah, it's the square root. So the squared function, you said that 4 times? You should have said it a 5th time so I could have heard you. No, sorry, I didn't hear you. Yeah, so the squared and the square root function are inverse functions. If you take a number like 2 and then square 2 and then take the square root of 2, what happens? What's your result? Yeah, 2 squared and you take the square root of it, you get what you started with, right? And that's true for any value. So, no, you don't need to write this part down. So when you take a function and apply that to a value, and then apply the inverse function to what you get, you always get the result, right? So in this case, if we go back, somewhere over here, if we take the exponential function and apply the logarithmic function, or if you want, take the log of x, and then take that and plug it into the exponential function, the log and the exponential should undo each other. That's what inverse functions do. They undo each other, right? You apply a function and then its inverse together, you should undo them and be left with your original input. So in this case, the log is one function, the exponential is the other function, and it's acting on x. So this actually just is going to result in x. And that's because the log and the exponential will undo each other. It is a little bit confusing. I would say that's probably the most confusing one of the bunch. I mean, there's 3 of them there, and that's probably the one is the hardest one to kind of notice. Yeah, there's 3 there, and we'll get into some 3 others that are a little bit more involved, and I want to show you where they come from. That's a really good question. I was just thinking that really this is the same as this written in the other order, right? So remember how I used the example if you take the square root of x and then square it? This is kind of like taking the square root first and then squaring it, and this one's like squaring it first and then taking the square root. You apply the function both ways and you get the result that you started with. So they are very similar. This one? This one? This one. I forget why I wrote that there. Oh, that's this one, right? Yeah. This one right here? Sure. Let's say we had, you don't have to write this down. I'm going to get rid of it, but let's say we had the log of 8. Nope. 8 is 2 cubed with base 2. This means 2 to some exponent is equal to 2 cubed. So 2 to some exponent has to equal 2 cubed. Yeah, so this has to equal 3. So that's kind of... I knew you were going to ask for that. Yeah, I know you do. Thank you for asking. So let's try this. 2 to the log of, let's say, well, let's stick with this 8. And we'll do this as base 2. Nope. This has to be an x. Sorry, let me start. I'm going to change that from a 2 to something else. Sorry, I just wanted to change that. I had an extra 2 there, and I thought that might get confusing because how do you know which 2 is which? But. So here we're going to apply the log function to 8, and then we're going to take that result and put it in the exponential function. That's like taking the square root of x squared. So the square root, and not exactly, but it's the same idea where you apply a function and then you apply the inverse. Those two functions should undo each other. The exponential and the log function are inverse functions. So this is 2 to the something, right? Like 2 to the x, that's an exponential function. This is the log function with the exact same base. And because these are inverse functions, yeah, so those two things are going to undo each other and just leave you with an answer of 8 or a result of 8. I just picked it as a number to use in the example. This 8 or this 8? The result? Here's the exponent, right? So you see that this is an exponent, and it's the exponential function is. There you go. Sure. Yeah, you can look at it that way too if you want. Sure. That's a good idea. Erin actually went even further and she said, hey, what is log 8 base 2? This means 2 to some exponent is equal to. So this has to be a 3. Well, 2 to the 3 is just going to be 8. That might be a better way to kind of help you with that. Yeah. Okay, so now we have to get in. So these are a couple of things, sort of observational things that, again, if you see some of this stuff, you can kind of simplify. You know, if you see a log a to the x with base a, that you can just reduce that to just an x and help you a little bit there. There are some sort of more formal laws that we have to get into. I will show you how to get one of those laws. Sometimes I kind of skip over this part, but I think it's not a bad idea to look at where it comes from. So let's look at what we call the product law. And just so you get some kind of frame of reference, we have a whole bunch of laws that deal with exponents. When we take one power and multiply it by another power and both have the same base, we have some rules for that, right? You take two powers with the same base, multiply them together, and that's the same as adding the exponents. Is that okay? Okay. Are you having a hard time with your pens or something?
I don't know. I just. Yeah.
So if we took 2 to the x and multiplied it by 2 to the y, we have some rules that deal with how to do this, right? What? Yeah, so we would get 2 to the x plus y though, right? Because you have to add the exponents when you multiply powers with the same base. And we have a division rule, and we have like a power of powers rule. There's kind of the equivalent because the exponentials are related to the logarithms. There are the equivalent laws. And here's the power law. The power law just says that the log of x times y base a is equal to log x base a plus log of y base a. This is like the same rule that we just talked about, multiplying powers with the same base, you add the exponents. Well, don't forget that these are the exponents. Yes. You mean these ones right here that aren't really the same size? Yeah, sorry about that. Is that okay? We're going to do an example, not to worry. We'll do an example of all of these so you can see how it works. Do you see how this is connected to this idea here? Do you see the connection here? This says that, hey, we would add the exponent. I mean, this is the exponent. This is the exponent. If we had this sort of situation, we would just get this.
What I don't get is that log A we get log A is x squared. That's for finding the product, so x isn't going to be exponent if they write it in exponential chaos.
X isn't the exponent, but this whole thing is the exponent, right? So a to the result of this is equal to x. I can show you where this comes from if you want. Okay, yeah, no problem. Let's do it. So in order to show you, and I won't do it for all of them, but I'll show you where this one comes from, and then the procedure for showing where the other ones comes from is very much the same. I'm going to start here by saying, hey, let's let m equal a to the x, and let's let n equal a to the y. M times n then is equal to a to the x times a to the y. Is that okay? Like, we're just going through a series of hopefully logical steps. It also means that we could rewrite, you know, using the exponent rules. This is really just a to the x plus y. Now here's the part that you're not going to like, but we're going to do it anyway. Right? Yeah. Right. So I'm going to take the log. Yeah, that's a good question, John. Yeah, there's no way to simplify. If these two things didn't have the same base, then we couldn't just do this trick here. It's not really a trick, but we couldn't go ahead and just say, hey, keep the base and add the exponents. We wouldn't have a rule for dealing with that. So we don't have a rule for dealing with 2 cubed times 3 to the 4. We would have to evaluate each of those and then multiply. Yeah.
2 to the 4 just leaves 2.
You could make them both over 1.
Yeah, so that would work. So that you're right. All of this hinges on the fact that these bases have to be the same. That's the only reason we can go from this step to this step. If the bases aren't the same, then we can't do that. And I've chosen them this way so that we can go through this process, and I can just show you where do these x's and y's come from up here in the logs, and you know, where do all those little bits and pieces come from. So I'm going to take the log. I mean, remember, we're trying to show why this statement here is true, the one about the logs, the product law, but I don't have any logs in this question. So I'm going to introduce some logs. I'm just going to take the log of the left side, and if I take the log of the left side, what do I have to do on the right side? I have to do the exact same thing. Right, the base is 10. Now we could actually take the log to any base. You know, if it's kind of like a rooting, we could take the square root of both sides of an equation. We could take the cube root if we wanted. We could take the fourth root. Same thing applies here. We could take the log to any base. It's easy to do log 10 because then we don't have to write a number in there as the base, and the work actually ends up being exactly the same. Okay, so we have that. Now, I'm going to work over here for a second. Is there a way that we can simplify this? Sorry, you know what? I said it didn't matter. This becomes a lot easier if we do it with the base A. Sorry, John, I just told you it didn't matter, but then I realized our next step here. Is there a way that we can simplify this right here? Remember, this means A to something has to equal A to the x plus y. Yeah, so this now has simplified to x plus y. And we're kind of getting closer. We have the log of one thing times another over here. We don't really have any logs over there, but we'll get there. And let me just, I'm going to clear off some space here so we can keep everything on the same page, because I think that's going to be useful. So remember that way back here, we said that m is equal to a to the x. Can you write that in logarithmic form? So the log, you got that part. The base is a.
Or m equals log, or x equals log.
Right. Close. So remember that when you write in logarithmic form, here's the base. The result goes here. And that is equal to the exponent. Is that what you said?
Yeah.
Sorry, I thought you said the other way around. And we can do the exact same thing for the other substitution that we made. We said that n was equal to a to the y. Again, if we write that in logarithmic form, we can say that the log of n base a is equal to y. We can just plug these now in over here for x and y. So we get that the log, just got really dark in here. The log of m times n is equal to x, which is log m base a, plus y, which is log n base a. I will never ask you to reproduce this, but I wanted to show you how mathematically we can actually get at this rule. Rather than me just saying, here's the rule, go ahead and use it. We kind of went through this process of making some substitutions, rearranging a few things. We did introduce a log in there, and we come up with this idea right here, which is the same as this. Is everybody okay? I mean, I did use different letters down here, but everybody okay with this idea here? That if we take the log of a product, it's just the log of the sums. I mean, that's a quick way to, the sum of the logs is what I meant to say. This right here. Remember that this means a to something, we don't know what that something is, has to equal this thing right here. It has to equal a to the x plus y. Well, if these two things are going to be equal, then the two exponents have to be equal. So this whole thing has to equal x plus y. So that's the product law. Let's do the quotient law. Again, I won't go through the process of developing it because it's almost identical, except, you know, in here you would get a minus instead of a plus. But other than that, it's the same. And then there's one more after that, and then we can do a couple of examples. So the quotient law just says that if you take the log of a quotient, that's equal to the law of the numerator, sorry, the log of the numerator minus the log of the denominator.
So it's adding, it's multiplying.
You got it. Yeah, it's exactly the same as the exponent rules, right? If you're multiplying, you add. Except kind of, yeah. And then there's one more. There's one called the power law. Mr. Falls taught you last year that you know how to use the log button on your calculator. This one that we're going to do next, the power law, is the reason why that works. Yeah, it's okay. We're going to go over it. Not today, but we will go over it next week. And what the power law says is that if we take the log of some number with an exponent, that's just equal to r times the log of x. So log of x to the r with base a is equal to r times log x base a. It's what happens is we're able to kind of pull this exponent down and bring it out front here. That's really what happens. So if you ever have an expression where you can rewrite the exponent, and that's why that I'll show you next week how to solve these equations, and we'll use the log button on your calculator. So let's do an example of each, and then I think I'm going to let you guys work. So let's simplify log 6 base 3 plus log 4.5 base 3. How can we rewrite number A here, or letter A? So we have the sum of two logs. They have the same base. This is the same as the log of the first one, the first number here, the 6, times the 4.5. And then 6 times 4.5. What's that, 36? Oh yeah, 27, thanks. It's funny, as I was writing it, I thought 27, and I thought, oh wait, yeah, 6 times 4 is 24, and then, yeah, I get you. Oh, we can actually take this further, yep. Yeah, we can actually take this further and figure out an actual answer here, right? This means, what is the exponent that goes on 3 to give us a result of 27? Yeah. And then we can go through the same process here with the second one. Here it's a subtraction, log of 48 base 2 minus the log of 3 base 2. We could rewrite that as a single log. Because of the subtraction. What's that, 16? And again, this means 2 to what exponent gives us 16? And the answer here would be 4. Any bets on whether the next one, the answer will be 5? I should start doing that, putting little like codes within the, see if anybody notices the patterns, hints to the tests.
Wait, you haven't already been doing that? So what if I missed something?
I don't know what you've missed. No, I'm just kidding. All right, let's have a look at one that's a little bit more complicated. So let's do the log of the cube root of 25 base 5. So there's a lot actually in this question. It doesn't look like it should be any harder than the others, maybe even easier because there are fewer terms. But, oh good, I'm glad you said it looks hard. But actually it's not that hard. The first thing that you should be thinking here, and hopefully you kind of got at this at the homework last night, is that this root sign is a little bit of a problem. So how could we express this cube root of 25 using an exponent instead of a root? Yeah. You learned it where? Oh, in data? Oh, maybe. I don't think there are too many negative exponents. You certainly do it in grade 11, so yeah. Oh, that's a good question. When you deal with exponents, if you're looking at the cube root of some number, we could write that as x to the 1 over 3. This number here out front becomes the denominator in your exponent. Say that again? Remember that the negative, good exponents questions here. Remember that if you had a negative exponent, that's the same as having, in this case, the 25 in the denominator with a positive exponent. So if you have negative exponents, you could just move the whole power from numerator to denominator or vice versa, and the exponent would become positive. Did that answer your question, Leslie? Okay.
Would x just equal 2 to the power of 1/3?
Oh, I don't know. You're way ahead of me. But yeah, I think so. Close, really close. Yeah, so Josh is thinking ahead here. He's looking at the 25 and he's realizing, hey, if we can write 25 with base 5 squared, then we're kind of on our way, which is right. But first, let's go back. See if I can go back. Look at this power law right here. If we have a base with an exponent, we can pull that exponent down out front of the log. So we can do that here as well. We can pull this exponent down here, and we get 1/3 the log of 25 base 5. And now we can go ahead and do what Josh was saying. The reason why we couldn't do what Josh was suggesting earlier is, remember, this is 25 to the 1/3. That exponent kind of binds really tightly, right? So we kind of have to. True. Good point. I suppose you could have done this though, Josh. I'm not trying to say that what you were suggesting wasn't right, but you could have done this, I guess, and maybe that's what you meant. So we just wrote 25 with an exponent of 2, or sorry, a base of 5 and an exponent of 2, and then you could just multiply these two exponents. The base is there. Oh, sorry. I wrote this base as a 2. It was a 5, right? So this means 5 to some exponent is equal to 5 to the 2/3. What does that exponent have to be? What's the log of 25 base 5? Just 2. So this becomes 1/3 times 2, which is equal to 2/3. So 2 different ways to kind of do the same question. So that covers all the logs. I mean, it looks like there are a lot. I mean, there were 6 in total. A couple of them, I think the quotient and product law were fairly straightforward. This power law is going to take a little bit of getting used to and seeing it. But once you get the hang of it, it should be fairly straightforward. And then some of the ones that we started with make sense. You know, I think this first one kind of makes sense. The second one might make sense, but that third one's going to take a little bit of practice. Leslie? Oh, yeah, sure. Finish this off? Sure. Are you okay with this idea, with the exponents of exponents? So again, this means 5 to some exponent. Well, or if you didn't want to use the law, you just think about, this means 5 to some exponent is equal to 5 to the 2/3. Yeah. So this exponent has to be 2/3. Is that okay, Leslie? You could. You certainly could. I like that you're asking for all kinds of different ways to do this. So Leslie's suggesting, hey, why don't we just pull this 2/3 out here, which we could do. Then we get 2/3 log 5 base 5. 5 to what exponent gives us 5? 1. So this right here is equal to 1. We get 2/3 times 1. This is the first time I've ever done that question 3 different ways. That's awesome. You guys are special. I don't know. Homework maybe on the weekend. Find the 4th way. All right, here's your homework for the pre-semi homework. Or you can bring it to semi, I guess. You know, take a little dance break, do some math. Lots of studies show that physical activity and learning go hand in hand. What's that? Sure, yeah. No, but there will be some cases, I think, when we're solving equations where you're going to have to use that one. Oh, good. Good. I don't even want to know.
Curling up. Tony, it's not funny. It is funny.
It's so funny.
All right, so there's the work for today.
Can I see my class?
I can show your mark, yep. Let me just turn this stuff.